can share my my iPad. So can you see the screen?
Yes, I can see well. I think
Okay.
okay.
Thank you very much. Thank you, Alexander, and thank you, Martin, for the invitation. In this talk, I'd like to talk about arc index and minimal grid diagrams of prime knots. So first, I will give some basic definitions and necessary terminology for this talk. And then there are two other parts. One is tabulation of prime knots by arc index. And third, minimal grid diagrams obtained from Dowco-Thiefless weight codes. A knot is a piecewise smooth, simple closed curve in space, three-dimensional space. Two knots, K1 and K2, are equivalent if you can move one smoothly in several steps to another. And a knot which is equivalent to the plane circle is said to be trivial or an unknot. So these four figures all are unknots. And plane figures, as above, are called diagrams. And the diagram has finitely many crossings where one strand goes over another. And the minimal number of crossings among all diagrams equivalent to a knot K is called the crossing number K, denoted by C of K. So the unknot has crossing number 0. The figure in the middle has the first has no crossing, the second has one crossing, and third has one crossing, and the last has 1, 2, 3, 4 crossings, but they are all unknots, and their crossing number is just 0. Sorry. If a sphere divides a knot K into two non-trivial parts, as shown in the figure, so you can confine one part in the sphere and the other part outside the sphere, and then you cut, and then you join the loose end along arcs of the near the surface, near the sphere. Then you get two non-trivial knots. In this case, we call it a composite knot, and otherwise you call it a prime knot. A diagram is said to be alternating if overcrossings and undercrossings appear alternatingly along the diagram. So a knot is said to be alternating if it admits an alternating diagram. So here, this one has, if you go along the circle, along the arc, you go over, under, repeatedly. But here, for this one, so here, the two ends are both under, and here the two ends are both over, and so here under, and here over. So this diagram is not alternating. So here I show first 7 simple, most simple knots. The 3 crossing knot and, 4 crossing knot, and there are 2 5 crossing knots, and there are 3 6 crossing knots. they are all having a minimal number of the, crossings. And this table shows the number of prime knots up to 16 crossings. And so in 1988, Hosty, Thitliswaite, Weeks published an article in the Math Intelligencer, and then they show that there are 1.7 million knots up to 16 crossings. And this list is, you can get this list from Knotscape program, which runs on Unix machine. The Dowker-Thitliswaite code is a sequence of integers. So if you start from this, and then you go along the knot in the direction of the arrows, and then you mark 1, 2, so 1, 2, 3, 4, up to 10, because it has 5 crossings. So at each crossing you have one odd number and one even number. So you list the odd number sequence in an increasing order, and then you put the matching the even number. Here the minus sign means that in the sixth crossing is under the odd number arc. So there are and then you take only this sequence of even numbers, and this is called Dowker-Thitliswaite code, and you can recover the knot diagram up to mirror images using only this Dowker-Thitliswaite code. So I will just call it an DT code from now on. In 1995, Peter Cromwell published an article about arc presentation and arc index. An arc presentation of a knot is a shape of the knot contained in the union of finitely many half planes called pages with a common boundary line. So you may consider these 6 half planes are attached to the z-axis, and the angles theta equals 0 to theta equals 5 pi over 3 are the angle in the cylindrical coordinates. And then if you put them together, you get this figure, and then it creates a knot. And then you read these z coordinates, and then you take this sequence. This is an arc presentation of a knot. Sorry. So, and then the minimal number of pages among all arc presentations of the knot K is called the arc index of K, denoted by alpha of K. There are several different methods to describe the arc presentation. First is a wheel diagram. So you look at the knot in arc presentation from the top of the z-axis. Then you only get these spokes, and then you put this the pair of the height of the endpoints on the z-axis, and that's called a wheel diagram. And you can also have a grid diagram. It's a closed curve which is composed of finitely many horizontal line segments and same number of vertical line segments, with the convention that the vertical segments cross over the horizontal ones. So here, this is grid diagram, and then you can interpret it as this knot diagram. So the vertical line goes over the horizontal lines. And then another useful method is using a chromal matrix. So it's a square matrix of zeros and ones, and every horizontal, every row and every column, there are two ones. And then if you join the ones by horizontal segments and vertical segments, then you get a grid diagram. And every knot has an arc presentation. So here, suppose you have this knot, then you can deform it without making extra crossings. You can make it to this rectangular type. And then it may, and then a horizontal segment may go over the vertical ones, like this. Then you simply make this twist, so that every vertical segment goes over horizontal segments. So this is a grid diagram. And then if you have a grid diagram like this, then and then for each horizontal segment, you pull the middle of this horizontal segment horizontally to an axis behind it. Then you get this. Then you have this 1, 2, 3, 4, 5 pages to embed this knot in 5-page arc presentation. So every knot has an arc presentation. So there are several useful theorems. So every non-trivial, so it's proved by Morton, Beltrami, and Babcock. For every non-trivial knot K, the arc index is not bigger than the crossing number plus 2. And the equality holds if and only if the knot is alternating. And theorem of Jin and Park, if K is a non-alternating knot, then the arc index is not bigger than the crossing number. So in the second part, I will describe how we tabulated prime knots by arc index. So there are 3 published articles. So first, so prime knots with arc index up to 10. So this work was done with a group of the gifted high school students. And then later, we tabulated up to arc index 11. And then later, prime knots up to, so in addition to the first 2, we computed arc index 12 up to 16 crossings. So the 16 crossings is the so the Hosty fixed rate weeks program, NASCAPE, gives us a full list of prime knots up to 16 crossings. So up to 16 crossings, each knot has a name, but beyond 16 crossings, there are no names. So to compute for the tabulation, we mostly used C program, and then we used a Linux shell to handle the text data, and then we used a NAScape to identify these knots again, and then we used LaTeX picture tool to draw grid diagrams. So we basically we generated chromal diagrams, old chromal diagrams, and then and to avoid duplicates, we used a norm. So norm of a chromal matrix of n square digits, matrix of n by n matrix is the n squared binary number, n square digit binary number, which is the concatenation of row vectors. So the arc index of smallest arc index for non-trivial knot is 5, the trefoil knot, which has crossing number 3. So for n between 5 and 12, we proceeded with the following steps. So we generated all n by n chromal matrices in the norm decreasing order. And then we discard those corresponding to prime knots. In some case, if we join ones, we may have such diagrams. This means this is a union of 2 closed curves. So this is not a knot. This is a link, and or we may have something like so in this case you can there's a sphere that divides it into 2 parts. That means this is a this is composite, not a prime. So we discard such things. So so we discard those not corresponding to prime knots. And then thirdly, we discard those reducible to smaller size. So we may have grid diagrams such as and then this part can be easily deformed to a smaller size. So we discard. So if we start from the n equals 5 completely and n equals 6 completely and so on, then you don't need to do to consider such things because these are already produced. And third, and then 4, discard the duplicates using row column moves, flips, rotations, and symmetries. So because knot diagrams can be so this one knot can have many different projections. So there correspond many different chromal matrices. So we discard duplicates. So the way we discard, so if you have 2 duplicates, so then one we throw away, and we throw away the one which has smaller node. And then in step 5, we identified the knot of the grid diagram by using NotScape. And number 6, we further discard if the knot already appeared for a smaller n, so on. So so this figure shows the figure on the left shows 3 consecutive pages in our presentation, and if there is an arc with 2 endpoints, and in between these 2 endpoints, there are no other endpoints from other pages, then we can just remove it. Remove the page by putting the 2 endpoints into the same point. So that in grid in Cronel matrix, this corresponds to a column with 2 consecutive ones, and then we remove that column, and then we add the 2 corresponding rows, and then put them together. And we did if there is the same kind of thing appear in a row, if we have a row with 2 consecutive ones, you can remove it, and then you can add the 2 corresponding columns together. And then the figure above shows the corresponding situation in our presentation. And if in Cronel matrix, suppose you have 2 rows, and then so if you join, so these ones in the 2 adjacent rows, the ones are not interlaced. So either so it's like 2 parentheses. So if you have so 2 parentheses. So if you something like this happens, this you cannot do this. But in this case, you can just interchange the 2 rows. And then this figure shows the situation in our presentation. And then there's a similar situation in for columns. So if you 2 columns, the ones are not interleaved, then you can interchange. And then the figure above shows the situation in our presentation. And then flipping, so you can flip this in the diagonal, and then that corresponds to taking a transpose. So when you take transpose and then you compute, if you compute the norm, and if the norm has been increased, then you throw this away, because this has already been handled, because we are working according to the order of decreasing norm decreasing order. And then taking mirror image, you just flip. If you take the mirror, so there is a mirror here. There's a mirror here. Then so from here to here is you just flip by a vertical line, about the vertical line. So these are the same nuts in terms of the DT code. And this table shows the number of prime nuts by crossing number and by arc index. So in the first 2 articles, up to 10 and up to 11, we computed, we made 12 up to 11, right? So yeah, so we listed all of these knots and their minimal grid diagrams. In the third article, we gave diagrams of this part. It's up to 16 crossings. And here, these numbers on diagonals, they are alternating knots. And by Haas-Dietrich rate weeks, we know these numbers. We know these number of alternating knots and number of non-alternating knots also. So we have we know them. So we know the list of sorry. So we know who them, but in the three articles we didn't include we didn't have this the diagrams of grid diagrams of these knots. So we know they have such arc index, but we didn't have. But in the third part, we have this list in grid diagram, and then we have the list of this grid diagram, and this one we are still working on, but we didn't try this part yet. Any questions so far before I go to the last part?
So if somebody has questions, then please either raise your hand or write in the chat. And Professor Jin has the right to unmute as somebody, if he wants to. Okay, this is how I organize.
I don't see all of the audience. I see only a few. Okay, so I'll continue. So in part two, we generated all possible grid diagrams, and then we throw away duplicates and we identify them, and then we sorted out in the increasing order of the of the size. So in this way we computed the arc index. But in part three, we worked on alternating 11 crossing alternating knot and 12 crossing alternating knot, and we know what they are, and then we know that we know their minimal, we know their arc index, but we didn't have arc presentations. So we found their arc presentations in the form of minimal grid diagrams. So so there are these two articles have the list. So in the this 11 crossing crossing prime knots, there are 367 knots, and 12 crossing alternating knots, they are 1,288. So here, for this part, we used the maple to write some procedures. And then we used Linux shell to manipulate the text data. And then we used Matplotlib to get DT code from grid diagrams. And then we use Netscape to identify them to confirm where we didn't make mistakes. And then we use LaTeX to generate the diagrams, the grid diagrams. So we used the method of Netscape diagram modified to filter the spanning tree method. So so if you have a C crossing knot diagram, then you can deform it so that there are same number of spokes. So here, here you have 1, 2, 3, 4, 5, and 6, 6 regions. So if you have a 4 crossing knot, you have 6 regions, and then you end up with spokes with 6. The field diagram with the 6 spokes. So you pick a crossing, and then you successfully deform the diagram so that it has only one crossing diagram, one multi-crossing diagram with a simple roofs. And then, but if you instead of contracting along an arc, you just draw that arcs. Then it becomes a spanning tree of this diagram, and then you add some extra arc, and then so this method is called filtered spanning tree method, and so we used this method for 11 crossing and 12 crossing or alternating knots. So the 11 crossing prime alternating knots have arc index 13, and we, with my former student Lee, we used the method of filter spanning tree to find minimal arc presentation of 367 knots, but we did it by hand. We found the spanning tree by hand. And then we used the Netscape to verify them. So here you have this 367 11 crossing knot and their minimal grid diagrams. And then for the 12 crossing prime alternating knots, they have arc index 14. So we wrote several procedures in Maple to find minimal arc presentation from DT code. And then we generated 1,288 grid diagrams and then verified them with Netscape. So this is the first, so number 1, 12 crossing alternating knot. So it's index 1. So starting from this point, this is crossing 1, 2, 3, 4, 5, and so on. And then this means crossing number 1 and 4 in the same make one crossing and so on. So this is 1, 3, 5, 7. As I explained it around the beginning, so this sequence corresponds to the odd numbered crossings. And because it's alternating, there's no minus sign in this DT code. And then I put, so I labeled the edges. Edge means the arcs between two crossings. So in the same order of the crossing numbers, and it's a 1, 2, 3, 4, and so on. And then we constructed, we found the regions. Okay, so for example, this region is, where is it? So maybe here. So it's starting from 15, 11, 19, 13, minus 6. So minus 6 means it goes backwards. So in the order of increasing number, so it goes backwards. The arrows are in this way, but this arrow is opposite of this numbering. The arrows by the numbering. So these regions are all coherently oriented by taking suitable signs here. And then we found some spanning tree, and this spanning tree has orders. It's a growing tree, and then it's a tree, so it's you can put it inside a circle, and then you can get this shape. So these two are equivalent. Okay, so it's equivalent, and then you. So this is the order of the spanning tree, and then the minus means from the root it goes backwards of the given orientation, and then so this is first starting from here. This is first edge, and then the next edge, and so on. So and then at the very end, you have to have one arc divided by 2 to handle the outside region. And then you can because these arcs will have horizontal level, and then you can adjust the level of these endpoints, and then you can read the arcs of the arc presentation. And then here, the leftmost edge. Sorry, so leftmost edge is has the level 7 and 11, and 7 and 11, so it's a 7 and 11 here, 7 and 11 here. And the next edge is from here, and the next edge is from here. So when you go around this circle, you can read all these arcs and their levels. Okay. So that's the background in the procedure. then so we get the DT code from NotInfo of Indiana University. It's so so these DT codes are actually from Netscape. Okay, but it's easier to get from NotInfo. And then you read this, and then you put sorry. So you get so the very first is 4.8. So this is the one we were I showed. And then from DT code to the oriented regions, DT to OR means DT code to oriented regions. So we so these regions, I showed you these regions. And then oriented regions to spanning trees. So this is a spanning tree I showed you with the figures. And then this is the arc presentation. And then from the so these are the 3D coordinates of the vertices, and it also draws plane figures and also three-dimensional figures, so that and then the coordinates of these three-dimensional figures is obtained from the previous slide. And then it produces some text data so that we can convert it to LaTeX picture commands. So this is drawn with this picture command of LaTeX. So this is so these two are produced using Maple the plotting. And then from the vertices of the three-dimensional version of the grid diagram, to identify this to confirm this is the original one. So we computed Darko code. We get Darko code from Matplot. Matplot is a very powerful tool programmed by Rob Schrein. He's a computer scientist whose thesis is this Matplot program, and then it was the famous knot theorist Dale Robson helped him guided in knot theory part. And then so from the so this is the 3D data, and then this is the command line to for the to so what is it? the docu. So this is a preparation to share command to work with NotPlot, and then this is the result of NotPlot, and then we sort out only the DT codes, and then we run this on Netscape, and then so we have this 12A1 knot. So back so this is how we compute it and how we confirm that the data is correct. So this is the list of 1,288 EDMR grid diagrams of 12 crossing alternating knots. So you may remember this diagram. So I showed you this diagram during the talk. Thank you very much. That's all I have.
Are there any questions? Okay, so let's thank the speaker again. Thank you, Professor Jin.
Thank you very much.
So, I guess there is something in the chat. Yeah, okay. So, and then thank you everybody for joining, and then we will continue the workshop this evening, 8 p.m. with Roland van der Ven. Okay, thank you.